We've been talking about thermodynamics all week, and at this point you're comfortable with some basic terms, calculating heat transfer, which is Q, talking about calorimetry and being able to perform those calculations to calculate, for example, the specific heat of a metal or unknown substance and then identify it. Last time we got into interpreting and calculating changes in enthalpy. Later on in the week, we'll get into entropy and free energy. And last time, we calculated the change in enthalpy under standard conditions for a reaction by subtracting the delta H's of formations of reactants from the delta H's of formation of products. And so this time, we are going to determine the change in enthalpy for a reaction using a different method known as Hess's law. And sometimes we need to do that because perhaps you don't have delta H's of formation available to you and you need an alternative way to do it. So if for some reason the delta H's of formation were not available, you might need an alternative way to calculate the change in enthalpy. And we talked about this the other day. Your delta H's of formation are on table 5 or the secondary table that I showed you, and you will be assessed on that on your quiz. Another way to determine the change in enthalpy for a reaction is by doing something known as Hess's law. This at first glance is going to look very, very challenging, but if you're very systematic in your approach, you will be highly successful with calculating delta H this way. There is a video that you may watch at home or after our lesson, and it just really hammers the points down similar to the way that we do it. I kind of like it better this way, but certainly for a second look-see, the video will be worth your while. So with Hess's law, it says the enthalpy of a reaction, that is delta H for a reaction, is the sum of the enthalpies of the combined reactions. So we had said last time that enthalpy is a state function. It depends only on the initial and final values. The path you take is irrelevant. When the bell rings today, you will go to lunch. It doesn't matter what you do along the way, but you'll all wind up in lunch in about 7 minutes from the time the bell rings. Now, because it is a state function and doesn't depend on the path, we can determine delta H using Hess's law. For example, let's say I want to determine the delta H for the reaction A to Z. So it's written there, and in bold-faced it's here. I want to figure out the delta H for that reaction from substance A to substance Z. I don't have delta H's of formation for A and or Z, so I can't just do products minus reactants. However, I do have delta H's for the process from A to M and then M to Z. If you can add these two reactions together and get your net or bold-faced reaction here, then you can calculate the delta H for the reaction by adding those two delta H's together. The sum of. Hess's law says that the enthalpy of the reaction is the sum of the enthalpies of the combined reactions. So using the sum of, I can get this. And when you're working this, if you see the same substance, that is M here, on opposite sides of two equations, and the coefficient is the same, then the M cancels. It would be similar to doing an algebraic problem where, for example, you have 3 equals x plus y, and you have x plus 4 equals y. If you summed these two equations together, these x's would cancel. If you don't see it, you could subtract x from this side, and then you see the cancellation. 7 is equal to 2y if I add the two equations together. So if you have the same substance with the same coefficient on opposite sides of two equations, they will cancel. If you have the same substance on the same side of the equation, you add them together. And if, for example, you had this where you're summing the two equations together, again, 3 plus 4 is 7. I've taken care of that. Y plus 2y is 3y. And now you've got 2x here and x here. The same substance, but the coefficients differ, so it would be 2 minus 1, and you would have x over here. And you'll see where this comes into play shortly. But you can treat Hess's law very algebraically. If you have the same substance on opposite sides of two equations and the coefficient is the same, it will cancel. Right, Riley? Absolutely. If, for example, you have this one shown at the top of your screen, the way I like to process these is I look at my net reaction, which is the bold-faced at the bottom. I want to figure out its delta H, its change in enthalpy. I look at my first reactant A. I see two A's here, and I see A here. Same substance, opposite sides of the equation, but I can't just cancel them because the coefficients aren't the same. 2 minus 1 leaves me with 1A here. I see 2B here. I've got a B, and I've got a B. B plus B is 2B. I have a C here. I've got one here. I've got one here. That makes 2 C's on the right and 1 C on the left. 2 minus 1 leaves me with 1 C on the right. I've got a D. What's so funny? I've got an E. And I've got an F here and here. So when I add these three equations together, I've got my net equation, which means to find this delta H, all I need to do is add up their individual delta H's. So if you can sum the equations to equal the net, you can sum their individual delta H's. So it looks really easy so far, right? All right, here it comes. It says sometimes one or more reactions must be reversed, which requires a change in sign for that delta H.
Why don't they just flip the triangle?
Alrighty. Here's my net equation right here. My approach is to start with reactant 1. I see it right here. So far, this first equation is looking good because A is a reactant in both and the coefficient matches. Reactant B is right here, and again, equation 1 is looking good. Here's where the trouble starts. Here's C, and the coefficient is 1, But C here is a reactant. And that suggests that I need to flip this equation around where product E becomes a reactant and these reactants become products. So from here to here, I have flipped this equation around, and when I flip the equation around, I change the sign of delta H. So whatever it was, we take the opposite. If it was endo, it becomes exo. If it was exo, it becomes endo. And now reactant D, which is right here, is right here, and that's a good sign. And I did use the same color here. I don't know if it was confusing to you. I apologize. I'll flip it right there. So when I add these two together, it's delta H1 plus the negative of delta H2. My approach is to look at the net equation, find the substances above, see if an equation needs to be reversed. If an equation needs to be reversed, I change the sign. In addition, before I go ahead and add the delta H's, I need to make sure anything not in the final equation cancels. 1E here and 1E here will cancel, and E is not in the next equation. It's important that you cancel out, otherwise you may miss something. Here's the last scenario, and then we'll work through 3 or 4 examples to make sure that you can calculate delta H for reaction, the change in enthalpy, using Hess's law. It says sometimes one or more reactions must be multiplied by some factor, and that requires that you multiply the delta H by the same factor. Make sure whatever you do to the equation, you do to the delta H. That's a common boo-boo. I look at reactant 1 in the bold-faced reaction. I've got an A. I've got an A here. Looks good. I've got a B. I've got a B right here. That first equation is looking like it doesn't need to be altered in any regard. I've got 4C here. So what do I need to do? I've got C on the correct side here, but the coefficients too. So from here to here, I tried to write in multiply by 2, but I couldn't write on the arrow. You probably want to. Multiply by 2. So you get 2E, 4C, and 2D. And now you've got a matchup here and here. You check the last product, and that is 2D and 2D. Now before I sum this together, when I multiplied this one by 2, I of course multiplied this by 2, and I want to make sure that anything up here that isn't in the net equation cancels. And the 2E here and here, same substance with the same coefficient on opposite sides of 2 equations, cancels. Now I sum these two together. It's the sum of, here's your delta H for the reaction. Now this can get messy because sometimes you'll need to both reverse the sign and multiply by some factor. And when you multiply by some factor, typically it's 2, 3, 4, 5, 6, although you could multiply by a third, a half, a quarter, a sixth, etc. I tried not to do that, although I gave an example just to show you. We're going to walk through a series of examples here. We want to use the following equations to calculate the enthalpy change for the net reaction in bold. We want to indicate whether the reaction is endo or exothermic, and we can do so by looking at the sign of the delta H of the reaction once we have calculated it. Alrighty. So I'm going to print this and write on the sheet so that I work it alongside you. Here we go. If you have a highlighter or 2 or 3, it may be a good technique, and I'll show you how I approach my problem solving. Anybody want to write on? I finally found what I was looking for. Here you go. Alrighty, here we go with Hess's law. So our goal is to determine the delta H for the reaction, not from delta H's of formation, but rather by summing the delta H's, provided that the equations equal to the net. The way I approach these problems is as follows. I've got reactant here, 2 moles of nitrogen dioxide. Where is that substance in one of these 2 equations? It's right here, right? So that means we have to reverse this reaction. I've got 2 NO2s yielding nitrogen gas and 2 moles of oxygen gas. I'm going to scribble this out and underline this so I don't get confused. And when I flip the reaction, what do I do to the sign? I make it negative because it was initially positive. Now I look at the product, which is dinitrogen tetroxide. Where's that? Right here. It's on the correct side. The coefficient matches. That suggests that that first equation is fine as written. Now I look for the cancellation effect. 1 mole of nitrogen gas on the left in the first, 1 mole of nitrogen gas in the second. On the right, cancel, cancel. 2 moles of O2 on the left in the first equation, 2 moles of O2 on the right in the second, cancel, cancel. Now when I add these 2 together, I get that bold-faced reaction as shown. And now I can add these 2 together and I get negative 24 kilojoules. The reaction is exothermic because delta H for the reaction is negative. And again, not on your quiz, but definitely on your test, easy 15 points. Questions on number 1. If you're very meticulous with this, you'll be very successful with it. Question number 2. Again, look at the bold-faced. Grab that first reactant. You see it here, and I already heard one of you. What are you going to do? Multiply by 2, a 2, a 2, and a 2. And when you multiply that by 2, you multiply this by 2 as well. Now the oxygen is a little bit all over the place. I'm not going to touch it yet because I'm not really feeling like I'm going to drive that home easily. I'm going to jump to the product. I've got 2 carbon monoxide. Where is that? It's on the left. The coefficient matches, but what do I need to do with that equation? Flip it around. I've got 2 CO2 yielding 2 CO plus O2. And when I flip it around, I now have it in the right location. And when I flip it, what do I do to this sign? I need to make it positive. And then Hess's law says if you can sum the equations, you can sum this. Let's make sure we have the correct cancellation. I've got the graphite. The 2 CO2s cancel. I've got the carbon monoxide. I've got 2 O2s on the left. I'm going to make a little chart here because it may be easier to see. I've got 2 O2s on the left and 1 O2 on the right. 2 minus 1 is 1. So that is good. You can do this if you want to get it down, but you don't really need to. And now I've got 2 times negative 393.5 plus, because this is no longer negative, so plus positive 566 kilojoules. And what'd you get? And you get negative 221.0 kilojoules, maintaining that 1 decimal place. And again, the reaction is exothermic. You got it, because delta H for the reaction is negative. Now on your test I gave you a problem that had more than 2, and at first you're like, oh, she's so mean. And I did that on purpose because you can get partial credit for driving some of the equations, but you also really have to focus on the net reaction. So let's take a look. I've got propane. First equation's looking happy. Oxygen's all over the place, not going to play there yet. I've got 3 carbon monoxide. Where's carbon monoxide? Yeah, it's on the left. So it's not on the right side and the coefficient doesn't match. One thing at a time. Flip it. And when you flip it, what do you do to the sign? Change it. But in addition to that, I also have to multiply by 3. 3 times a half is 3 halves. And I'm going to multiply this by 3. You may want the parenthesis here. Maybe that would be better for you. Alrighty. And then the water molecules, oh, they're good already. Let's see if we can figure out what's going on with our crazy oxygens. We have 5 O2 here and 3 halves O2 here. 5 is the same as 10 halves. This is on the right side, so we will subtract to get 7 halves. And now we can add these 2 together, and we have negative 2219.9 plus 3 times 283, and that is negative 1370.9. And actually I jumped the gun a little bit, and on this one it's not going to matter, but on a subsequent problem it could. So I do want to go back and reiterate. It's very important that you cancel anything that's not in the net equation here. Make sure you go back and cancel as we did everywhere else. So those carbon dioxides must cancel, and that will be particularly important in number 4. So again, before you sum it out, make sure you go back and cancel, especially when you've got a reaction you haven't really touched at all. You've got to make sure that everything cancels that's not in the net equation. So be sure to cancel the CO2. And again, this reaction would be endo or exo. Exo because delta H for the reaction is negative. Number 4 is kind of hard. I'm going to let you try number 4. Well, you want to try it or you want to do it together? Together? Okay. Here's my approach. This one's just a little sneaky because you've got fractions in there. Here's chlorine gas right here. That suggests I need to multiply the first equation by half. And when I do that, I'll multiply this by a half. Sodium bromide, but the coefficients don't match. I've got 1 here, 2 here. What do I need to multiply the second equation by? 2 times 2 is?
4.
What times 2 is 1? 1 half. Cancel, cancel, because those will both be 1s. A half and a half, so I have to multiply this by a half. Here's sodium chloride. And here's the half of bromine. So at first glance you're like, woohoo, I'm ready. But this is where the cancellation is particularly important. You've got an equation in the third one that doesn't seem to play a role in the net reaction, but you still need to make sure that you're getting cancellation of any substance that's not in the net equation. So I can see here I have half a mole of calcium oxide, but I've got 1 mole of calcium oxide here. So what do I need to multiply that last equation by? You've got half a mole of calcium oxide here and 1 mole here. I need them to cancel. So I need to multiply this equation by 1 half. And that's where I said make sure everything cancels. And when you do that, you'll multiply this by a half. Now these cancel. This cancels. This cancels. And this cancels. And now the only things remaining are our reactants and products. So again, before you process it, make sure every substance not in the net equation cancels. That will be important. And now, as you walk through, your delta H of the reaction is the sum of all of these, which is negative 53.0 kilojoules. And again, this reaction is exothermic because the delta H for the reaction is negative, as we wrote up above. I try not to play with fractions too much. It's a little bit tricky, but you certainly can have a problem with 3 or 4 equations. And if you're very meticulous in your approach and you make sure everything else cancels, you should be highly successful here. Hess's law says that you can calculate the change in enthalpy by summing the enthalpies of the reactions that you combined. Questions here? It takes practice. On your classwork, the one you already have, numbers 10 through 12 deal with Hess's law. Number 12 is sneakier than anything you'll see, but if you can do that, you're in good shape. Kids told me in a previous year that they needed more practice on this, so I have generated this classwork for you. You want to do 1 through 4. The answers are on the back of the sheet, which I'll give you now. This will be assessed on your exam, which I believe is scheduled for late next week. But your quiz only goes through enthalpy determination like we did yesterday. Hess's law. It takes practice. If you do the 7 problems I've given you, and then you do them again when you're studying, you will be very successful with Hess's law, and it will serve you well for those of you moving on to any college chemistry class. So we've got the change in enthalpy. Next week we'll be getting into entropy and free energy and closing out the chapter. Questions?